So today, what we want to look at is we want to look at the difference between a chi-square test for homogeneity and a chi-square test for independence. So these are the two types of tests that we looked at last class. And the AP exam really lately has really harped on the difference between those two types of tests. So when we're dealing with the chi-square test for homogeneity, we're looking at one variable and we're seeing, is that one variable the same in two populations? So homogeneity, you have two populations and you're measuring one variable. A chi-square test for independence asks whether there's an association between two variables in one population. If we wonder whether the distribution of eye colors is the same in the US as it is in Canada, we'd have two separate random sample of people from each country. Those are our two populations. And then we would survey each person about their eye color. That's our one variable. That's a question of homogeneity. As opposed to if we wonder whether there's an association between eye color and handedness. Here we're measuring two distinct variables. We'd probably choose a random sample of people from one population, and we would ask them those two things about those two variables, their eye color and which hand that they write with. That's a question of independence or association. So when you see chi-square test for independence / association, those are the same things. And then you have your chi-square test for homogeneity. Remember, on the calculator and the steps for running these tests are exactly the same thing. So we're going to look at an example now, and we're going to run the test just one more time so you have an idea of what it is. So a random sample of 200 students was selected from a large college in the US. Each student was asked to give his or her opinion about the following question. Each response was recorded in one of 5 categories, and the gender of each selected student was noted. The data are summarized in the table below. So we have one population here, and we've asked them two things. We've asked them their response to the question, and then we've recorded their gender as well. So this is a chi-square test for independence. The other way you know is if you look at the stem of the problem here, they're asking, is it dependent on gender, which is a kind of a giveaway that it's a chi-square test for independence. So we want to start by writing our hypotheses. So we're going to write our null and our alternative hypothesis. And I'm going to start with our alternative hypothesis, which is going to say that that response is dependent on gender. And then our null hypothesis would be that response is independent or is not dependent on gender. So in essence, what we're seeing here is there an association between someone's gender and their response? Basically, are males more likely to say they agree, or females more likely to say that they agree? That's our goal here of this type of test. So after we do that, we're going to check our conditions. Condition 1 is our randomness condition. Is it a random sample or random assignment? Here we've got a random sample. And you might have random assignment in these types of questions as well. But here it's a random sample. And then condition 2 deals with our expected counts. So now we have to do the most annoying part of this, which is checking our expected counts. So in order to do that, we're going to need our row totals and our column totals. So we surveyed 100 people, 100 males, and 100 females. And if we look at our column totals, we've got 30, 40, 40, 50, and 40. So if I make a table of my expected counts, Just to show you what the first cell right here would be, we would take 100 times our column total of 30 divided by our overall total of 200. That's going to get you 15. If we keep going here, these all happen to be whole numbers, but if they weren't, you would not round them. So our next cell is going to be 20, 20, 25, and 20. And again, we're taking our row totals. So our row total times our column total divided by the overall total, which is 200. And these end up being the same exact thing here. So we've got 15, 20, 20, 25, and 20. So each one of these little things here, these guys here, make up your chi-squared. If you were to sum up each of these little things, they'd get you your chi-squared test statistic, which we'll get later on. But we can see here for our second condition that all expected counts are greater than or equal to 5. We are going to run a chi-squared test, and you could call it for either association or independence. I'm going to call it independence. So into my calculator, this whole thing here is going to go in matrix A. And then this whole thing here is going to go into matrix B. And that's under second and inverse x, if you've forgotten where that is. So I put in all my data in there, and then I go over to stat, over to tests, and letter C, which is just a chi-squared test. Copy down your chi-squared test statistic. For this particular problem, it's 8.92. Your p-value is 0.06. And your degrees of freedom here are 4. We know the degrees of freedom by taking the rows minus 1 times the columns minus 1. From this point, compare your p-value to the common significance level of 0.05, and you're in a fail to reject the null hypothesis. I've sort of run out of room here, but we're failing to reject this, which means we do not have evidence of the alternative. So we have no evidence that response depends on gender. And that's a chi-squared test for independence. A little bit messy here, but hopefully you can follow along.